Today, this is so you've been doing some observations and you've seen some stuff. You come up with some hypothesis, something. Um, and but today, this is like the great reveal on why things do what they do. Okay, so here we go. I will give you a hint. Magnetic field lines form loops. Tell your neighbor. Okay, correct answer is B. Okay, so out of north into south, um, this is what you measure. This is what you observed, and with the compasses. Okay, out of north into south, but they continue to form complete loops and go from south to north on the inside. Okay, here's the warning. There is a distinction on which way the magnetic field lines go on the exterior of the magnet, which is what you observed in the lab, versus the inside. Outside goes out of north into south, but on the inside of the magnet, it continues to go from south to north. So watch yourself on that. Does that make sense? Make complete loops. All right. So electric charges and magnetic poles have some similarities, but they are in essence different. Okay. Yes, likes repel and opposites attract, but that's kind of where it stops. So this is an example of a dipole. You might have heard that in chemistry. There's two poles, positive and negative. Magnets are dipole, they have a north and south pole. With charges, you can have a monopole, meaning one. You can just have a positive charge and that's fine. We're not breaking any physics, it's just a proton just sitting there or something. To date, we don't know of anything that has a monopole for magnetism. They always come in pairs. They always has to be a north and a south pair. Okay, so that's usually the main difference people give. Like, what's the difference between? Can't have a monopole magnet. Correct answer is D. Those ferromagnetic elements are iron, nickel, and cobalt. The ferro has to do with iron. I don't know if that's Latin or Greek for iron, but it's one of those. Okay, so anything that has iron, nickel, or cobalt can be attracted to a magnet. Okay, in the case, steel is by far the largest metal that we find around, and that's a compound with iron in it. Okay, so what about what's going to repel a magnet? Correct answer is E, only other magnets. This is similar to charges, where if you have a neutral object, it'll polarize and it'll attract to a charged object. Or opposite charges will also attract. The only thing that will repel is the same charge. This is true here. The only thing that's going to repel from a magnet is another like pole. So two north poles, two south poles. Okay. So where we find our ferromagnetic elements is not a coincidence that we find them located in the general same location on our periodic table. So you had your 1s, your 1d, 2s, 2d. Okay, so we're categorizing electrons. I don't know if you did that. I did this in high school. I don't know if that was a thing you did more. And for electrons, it would be like spin up, spin down, spin up, spin down, spin up, spin down, spin up. Do you ever do that? Like categorizing? Huh. You're right. Good call. Thank you. It's been a while since I had chemistry. Okay. So here's the deal. At the very foundation, moving charged particles create a magnetic field. Okay. Moving charged particles create a magnetic field. Electrons spin, just like the Earth spins in 24 hours. That creates its own magnetic field. But usually when electrons are formed or like go into an atom, they have opposite spins. One's a spin up, the other one's a spin down. And those two magnetic fields that they create cancel each other out. And that's usually what happens. However, for nickel, iron, and cobalt, their valence shells I don't know how many, but have unpaired electrons that all have the same spin. So there's a net magnetic field for their atom or for their molecule, depending on what's going on. And that is why they can be magnetized. Okay? So that's at the heart of it. So let's say we take a hunk of iron out of the ground. The atoms or the molecules that form a crystal lattice, and this crystal lattice actually has little pockets called domains. We'll call them like magnetic crystals, and each crystal has a certain magnetic orientation. It has its own north pole here, north pole here, north pole. Okay, and it's randomized, it's scattered. But if you take that piece of iron and you stick it in an external magnetic field, some of those crystals, the ones that are going in the same direction, get strengthened. Those that are going in the opposite direction get weakened. Some of them actually switch, like rotate and into the direction of the magnetic field. And if that field is strong enough, or that piece of iron is exposed to that field for a long enough time, those domains switch and you get a magnet. Okay, so this would be a model of an example of just a hunk of iron that we pulled out. This would be the iron has now become magnetized, or the domains are more ordered in the same direction. Okay, so a popular question is like, well, what came first? Like, how did the first magnet come to be? That's, you need an external magnetic field. The Earth has its own magnetic field, and the first magnets were naturally occurring due to when they were like being formed, like cooled with lava or something. Those elements or those crystals formed, lined up with the Earth's magnetic field. That was like the first ones. Okay, so these domains, those magnetic crystals, are in the order of 20 micrometers. So I just wanted to give you just an idea. So I don't know what you saw in biology under a microscope, but here's a paramecium. Okay, skin cell, red blood cell. So this is the same length as this. So these crystals are somewhere between a skin cell and a red blood cell in size. So they're microscopic, but not crazy microscopic. Like you can see them with a normal microscope. Cool with that? All right. So in lab, you discovered that became south, that became north. But why? So the magnetic field of this magnet goes out of north into south, out of north into south. These magnetic crystals, these domains, are in this external magnetic field. And so some of them start to switch in line with this external magnetic field. So if you remember, field lines go out of north into south, but inside the magnet, they go from south to north. In the nail, the field lines, magnetic field lines, are going from south to north, making this side the North Pole, this side the South Pole. You do that. And then rubbing the nail. Make this bigger. Real big. Okay, so inside the nail, we're going to say that domains cannot migrate, but they can rotate. Okay, so in this orientation, just holding it here, the south poles of the domains are like, ooh, North Pole. But as we drag this across, the south poles are like, as they drag it across. Does that make sense? And so what you get, granted these are over exaggerated, after you've dragged them across, these magnetic crystals are oriented or arranged like that. And what you end up with, South Pole here, North Pole here. Good with that? So give this a shot. Have a conversation. Correct answer is? Correct answer is D. Dangerous dinosaurs. Okay. Here's the deal. The South Poles on this one are like, oh, and as you drag it, this side becomes south, this side is north. Here, the North Poles, whoops, are attracted, and as you pull it this way, the North Poles line up, making this north and this south. The way I remember it is wherever you end up has the opposite pole. Okay, good with that. Is everybody good with C? Next two magnets. Okay. Until what point? Like, until we are like at the atom level or molecule level. So another popular question that comes up is, why are certain magnets stronger than others? Correct answer is all three of these. Okay. The more domains you have, they're adding more and more to the magnetic field, the net, the total magnetic field. Okay, so bigger magnets of the same material are going to be stronger than smaller magnets. You could have a higher percentage of domains, like it's more organized. The more these are looking more uniform, the stronger the magnetic field is. The less organized, the weaker the magnetic field. Okay. And you could also have certain material has more, their atoms are more densely packed, and so you have stronger magnetic field. Rare earth magnets or neodymium magnets. Remember those magnetic BBs that used to be a thing, like, I don't know, in elementary or middle school? Put them together, really strong magnets that were like small balls. Those were made of neodymium or rare earth magnets. The magnets themselves were not silver. That was just a chrome plating. If you scratch that off, the magnet itself is kind of like a clayish charcoal color. It's crumbly. So that's the material. They're super strong for their size. Okay. Can you make a magnet weaker? Yes, by heating it or beating it against something. Okay. Both of those things are going to cause those magnetic domains to get scrambled. You heat it up, it's like they vibrate, scatters them, randomizes them. Hitting it against something also causes that. That's why I kind of cringe at people who drop a magnet. I'm like, ugh. Every year I need to remagnetize those silver magnets. Those are really weak, and they get unmagnetized pretty easily. Sometimes I have to do it multiple times a year, depending on how many times kids drop it. Okay. All right. So the big question: what is going on with the Earth? So on page 1, which magnetic pole of the Earth does the northern tip of a magnetic compass seek? If that didn't make you go, huh, then you were not engaged in the lab. If you just rolled with it and you're like, okay, you're either copying or you weren't thinking. You're just doing. In lab, your compass pointed this way. But it's supposed to point north. But it points south. But it points north. Because the geographic North Pole, where Santa Claus lives, where North Star, Polaris is located, is actually the south magnetic pole of the Earth. Okay. Now, a great follow-up question is like, why? That's stupid. It's a better reason than Ben Franklin declaring positive thing like electrons are positive. Okay. Here's how this came to be. So back in the day, ships were the main form of transportation if you had to go long distances. You navigated using the sun and the stars. On a cloudy night, you didn't have a hope. Like you just had to put your sail down and just wait for the sun to rise. Like, oh, that's east. Okay, we can start sailing again. Chinese discovered these naturally occurring magnets called lodestones. There's chunks of iron ore, and they found that if you put it on a piece of bark or wood and you floated it, it magically pointed towards the North Star. That was a huge breakthrough. It was like ancient GPS. All of a sudden, you could start sailing on a cloudy night. It's like, woo, I know which way is north. Okay. Does that make sense? Now, if you are a salesperson and you're selling, so a compass, all it is a floating magnet. You guys are right with like from what you did, like that's all a compass is just a magnet that's able to pivot. How would you sell this thing? What would you call this? Hey, this cool little indicator thing, it points to where north is. No way. Yeah, this point here, this painted part, we'll paint it just for, like marketing purposes. This painted part points north. No way. Prove it. See? Points north. That is the craziest. What do you call it? Oh, this is the north seeking pole. This points north. This points north. This points towards the North Pole. We're just going to call it the North Pole of the compass. It seeks the North Pole. It goes towards the North Pole. We knew what the North Pole. We just call this the North seeking pole. It's the North Pole of the magnet. It's abbreviated North Pole. It's the North Pole of the magnet. of the compass. No one ever thought, what happens if we bring two compasses together? That's a waste. I already have one for my ship. Why do I need two compasses? They didn't know how it worked. They just knew it did. And so later, when people started exploring and trying to figure this out, I was like, that just like, oh, wow. Because this is just the North Pole, and that's the South. It's just a magnet that's able to pivot. And so just because of the way we called these things, which made sense, the North Pole has to seek the opposite, which is the South Pole. So the magnetic South Pole is at the geographic North Pole. Ben. They, if you bring in another compass, and let's say somehow you could force it to point this way, North Pole, South Pole, they will repel, and it will flip to the point where it attracts. South Pole, North Pole. Does that make sense? Okay. So, um, there's a distinction between the geographic pole of the Earth and the magnetic pole of the Earth. Please be careful with what you're being asked. Okay. Now, to make things even a little crazier, the magnetic uh, South Pole isn't located exactly at the geographic North Pole. It's tilted slightly. So if you ever take an orienteering course, there's something called true north, which points towards Polaris, the North Star, and then there's magnetic north, and that's which way your compasses point. Okay. And to make it even crazier, that location of the magnetic North Pole or South Pole is changing. Okay. So, um, 70 years ago, it's over here, and it's moved and it's actually speeding up over time. The location of that. What's even crazier is the magnetic poles actually flip flop periodically. Now, um, good question. Why? So the theory is we're not 100% sure, but the the magnetic field we're pretty sure it comes from the moving iron in the mantle, creating a magnetic field. Why it flips, I don't know, but it does. We can look through geographical layers or geological layers and see the magnetic orientation. Um, so the white represents transitionary, north south. The black represents stable. Okay. Um, we've been stable for a long time. Does that mean we're due for a switch? Maybe. I mean, notice there's not a great like periodic pattern. It's kind of. Does that mean the end of humanity? No. It still provides. There's still a magnetic field that protects us from the Earth, or sorry, from the sun. Um, like it would be newsworthy if that happens, but it's not going to be like the end of humanity. And it's not, like some of those switches happened quickly, like 100 years. Some of them took a long time, thousands of years to switch. So It depends on how quick it would happen. Well, even quick, it's not much. Like anything that's oriented based upon the magnetic field of the Earth would definitely be altered. Um, but no, would not be changed. No, levitate with magnet like north and north and frictionless. Mm-hmm.
Well, then everything will be messed up. Wouldn't that mess up everything?
Not everything.
I mean, like, that's everything based on magnets.
Sort of. I mean, you'd notice I'd have to change my slides, but it wouldn't be like right. It I don't think it would affect too much of life.
What?
I don't think people.
Everyone
Sure.
learns never eat soggy waffles. Like now it's all messed up.
No.
Can't learn that.
No, you can still say it's geographic north. It's just the compass would point. They'd have compasses would have to be painted the other way, or they just say it's pointed south. All right. So last question. We'll call it good.
Yeah. All the roads would be messed up. Well, they say a bit of an exaggeration.
That's geographic north.
It's still north. So, but it's like
It'd actually be better for us.
I don't think I do either. I think I don't know what mine is.
Tell your neighbor.
I don't know. I just don't know. I know. We'll just turn back this direction. I think I can do a lot. I don't know. I think my ones are definitely real.
Correct answer is B.
What?
Okay. So this is the north seeking pole. This is the south seeking pole. Here's Santa Claus land. This would point towards the geographic South Pole because the geographic South Pole is the magnetic North Pole.
So then isn't it A?
No. What geographic direction? South. If I say what magnetic pole would that seek, that would be north. But what geographic? It points south. This is North Star. This is the Southern Cross. It's going to point, this guy's going to point towards the Southern Cross. It's a constellation you can see in the Southern Hemisphere. What?
Does the South Pole move too with like the North Pole?
It does move. It's not a perfect pair. Like it's not like.
Of course it's not. Why would it be?
It's a little crazy.
I'm so bitter. Okay, so you're saying that when they point in the same. But the question, like that's not saying the same thing. The south pole of the magnet is pointing in the north direction.
It's pointing to the north magnetic pole, but it's pointing towards the south, geographically.
So you're saying like that the stuff moves from South Carolina to South Magnet? I just don't like it.
Stuff moves. So the magnetic field lines go out of north into south. I don't know if this is what you're talking about. So it lines up this way. It's pointing towards the south magnetic pole. So the south is pointing towards the north magnetic pole. Because the north magnetic pole geographically is southward. Okay.